Hi everyone, welcome to 137th Stanford MedAI Group Exchange session. This week we have Mohammad Mostafijur Rahman from University of Texas at Austin here with us to talk about his work on efficient AI for biomedical imaging. Mustafi is a PhD candidate at the University of Texas at Austin, specializing in AI-driven biomedical imaging. His research enhances computational efficiency, addresses challenges in annotated data scarcity, and improves robustness and generalizability in medical image segmentation, synthesis, denoising, and classification. He has received prestigious honors, including the Summer IRTA Fellowship from NIH Office of AI Research, the Texas Health Catalyst Award, and multiple Best Paper awards. So, Mustafi, thank you very much for joining us today. Before we start, do you have any preference on how you would like to take questions? Can we interrupt you in the middle, or do we have designated breaks in your talk?
Yeah, thank you, Amara, for introducing me with the audiences. It's fine, like if someone would like to ask question like in the middle. So maybe after one topic or one paper, we can actually ask for the question and then we can proceed to the next one. Or I'm fine with even like at the later stage as well.
Okay, thank you very much. So I'd ask audience to just wait until the end of one topic before putting their questions forward. Thank you very much, Mustafi. Let me hand it over to you.
Yeah, yes, sure. Thank you so much. In my today's talk, I will be introducing some of our work on efficient AI for biomedical imaging. So reducing competition and data burdens or data demands. Mm, sorry, yeah. So in my today's talk, I would like to introduce first you with some of our advanced decoder architecture design for medical image segmentation. And then in the second part, I will be introducing with our two of our recent works, one data efficiency and model robustness. So as like there could be like audience from diverse backgrounds, I would like to first introduce the medical image segmentation. So what is medical image segmentation? So it is one of the semantic segmentation application or where we try to segment objects in an image. So object means in case of medical image segmentation, it could be tumors, cancerous lesions, or normal lesions, or other biomarkers, even could be organs. So if you see this image, so it contains different kind of tasks, so binary task to even in a multi-organ segmentation task. And our goal is to assign each pixel in an image a class level. So the class level could be, in case of binary, it could be 0 and 1. If you see like B polyp segmentation, so we'd like to segment this red cursor part. So this is polyphase. So our goal is to actually segment this part here. It's white, so that like doctor can use this for diagnosis and make the early diagnosis of polyp, so that we can reduce the death at the end, also like actually give the patient cure. So what are the like major methods or like main methods for this kind of semantic segmentation or biomedical image segmentation task? So before the emergence of deep learning, so there were traditional methods those are used for segmentation tasks. But after the emergence of deep learning, around 2015, unit architectures is one of the transformative methods that came in, and um, we are actually using different extensions of unit right now that tries to improve the efficiency or accuracy, or even both efficiency and accuracy for medical image segmentation. So let's have a look into the unit architecture. So unit architecture has an encoder. So the purpose of the encoder is to extract feature from the input image. So it extracts different resolution features from different stages as it actually downsample after few operations, and then we extract again features. So we have different resolutions feature from the encoders. So it actually start with the low level features to end up with high level features, and then we send the high level features to the decoder. So the purpose of the decoder is to reconstruct the output segmentation map that we'd like to um, get from the image. So each pixel have a output class level. So in this case, we start with the very high level features from the encoder, and then we refine the feature maps and upsample and do this progressively, and then finally we get the outputs. However, there is one challenge with this, that is when we start with the high level features from the encoder, we may lose fine-grained information. So to flow the fine-grained information from the encoder to the decoder, unit architecture introduce the skip connections. So the task is to, our job is, or purpose of this skip connection to flow the information from the encoder to the decoder, so that if we lose high level information during the refinement process in decoder, low level information or fine grained information during the refinement, we can get that through this skip connection. So what are the major challenges in this kind of architectures? First one is computational inefficiency or heaviness. So most of the cases, U-shaped architectures, even basic one, like having 50, 60 millions of parameters, sometimes even more. So even when we use the transformer for this, it may actually have more parameters and flops. So our goal is to, in case of medical imaging, it's crucial to have efficient solution to make real-time diagnosis. So this is one of the major research area that we can address, and in our some of work we address these inefficiency challenges and come up with solutions. And next, it's the data scarcity, one of the known challenges. So scarcity of annotated data here actually. So we may have access to larger volumes of data right now, but the annotation for segmentation tasks specifically is very much challenging. So we need to come up with solution that can utilize unannotated data, or that can utilize the subset of annotated data that could be representative to all other data. So this is one of the research directions that we can focus on. Some of our work we try to focus on this. So next challenge is robustness and generalizability challenge. So where in medical imaging or medical image segmentation, so we need the solution that work on different kind of races, different kind of medical devices and modalities. So our algorithm need to be robust and generalizable to different kind of situations and scenarios. So there's one of the thing we need to tackle in our when addressing the research problems. So addressing this, we have a few contributions that I would like to explore in my next slides. So first, I would like to introduce you with our very first method. So it's cascaded attention decoding. We presented this paper in winter conference on application of computer vision. So here we actually try to get the best of both vision transformer and CNNs. So vision transformer can capture long-range dependencies through self-attention, but the long-range dependencies are captured between tokens or passes. So that can actually limit the ability to learn the local relations among pixels. Although like some vision transformers try to use positional encoding or embeddings that may not fully address this concern. On the other hand, CNNs can capture a special relationship among the pixels through convolutions, but it has limited ability to learn the long-range dependencies like vision transformers. Additionally, vision transformers usually have higher computational cost and they're heavyweight than CNNs. So addressing or combining the best of both of these, we come up with our architectural design. So where we introduce a fully convolutional decoder that works well with transformer encoder. So we utilize the hierarchical transformer encoder where we can use any hierarchical vision transformer or even CNNs or even Mamba right now, state space models. So, but we need to have hierarchical structures having different resolution feature extraction from the encoder, and it could be pre-trained on ImageNet. We recommend that, and then we extract the features and we come up with our decoder. So we actually develop this decoder. So the core of our decoder is our cascaded attention module, where we have channel attention, we have spatial attention, and followed by a convolution block. So the purpose of channel attention and spatial attention to focus on a specific region or specific channel in the feature maps, and convolution block refine those attended features. So we use this cam in all different stages of our decoder, and we also utilize the attention gate to fuse features from the encoder with the refined features of the decoder. But in this case, attention gate helps to um, get only the relevant information. So this is actually attention gating. So gated signals are combined with the output from our refined output from our CAM module and up convolution of after the convolution operation, and we get four different outputs: P1, P3, and P4. So and in our experiments we try to utilize all these outputs as a deep supervision, and also combine them during the inference as well. So here is some of the feature visualization of our method. So we have the image and we extract features x1, x2, x3, and x4, and then the x1 is the high resolution feature or fine grained features from the encoder. But if you see our refined feature mask at the end of the decoder stage, so it can attain the polyp region very well, but the encoder feature cannot actually attain the class level information in that case. Our goal is to actually identify the polyp. So our refinement shows like it can actually do that job at the end. So but we start with the X4. When we start with the X4 and we get after the channel attention, spatial attention, and convolution block, we get the features that try to incorporate some level of like attention in other parts and like different kind of things, and after progressive refinement in every stages, and also like attention gated fusion, finally we get this attended outputs that has very good overlap with the ground truth in our final output as well. So here is another comparison that shows how our cascade features and traditional cascaded upsampler used in unit architectures work. So if you see here, so our cascade, it has the feature maps here. So if you see the final feature map, so we have more attention on the polyp region, but the traditional upsampler doesn't have that. So it has even ended up with false positives. Yeah, so in the next slide here, I am actually introducing you with actually one of the empirical observations or findings we have seen. So when we actually use multiple loss and multiple outputs, for example, 4 loss and 4 output, it start with very high dice score even after single epoch, and within a few epochs, 7 epoch, we get very higher dice score that's close to the optimal dice score in this model. And if we use just a single loss, for example, 1 loss and then 1 output from the final stage of the decoder, so it started with very low dice score, less than 40%, and it required around 18 epochs to reach this kind of dice score that we get in 7 epochs by 4 loss and 4 outputs. So this finding shows that the deep supervision helps to actually give like faster convergence of the model. So here is the different components evaluation of our cascade, and if we see this, when we use all these components like cascaded structure, like progressive refinement, and then attention gate and convolutional attention module, all this together, we get the best dice score in 5 different polyp segmentation test sets. Although like different module has different kind of effect on the segmentation performance. Yeah, so that's all our past contributions.
I think, Mustafi, we have a question from the audience. In case of polyp segmentation, intuitively speaking, why long range attention is important?
Yeah, so the thing is when you actually do the polyp region could be small, but in the image there might have like even multiple polyps. Even like polyp can spread through like very large regions, so larger polyps. So if you like to actually segment the polyp in a like if it's like a single region, so long range relation may help from one end to the other end capture so of the image. In that way, our model learn which part is polyp and which part is not polyp. If in case of classification, you may say, yeah, long range may help, but in case of segmentation also helps because we may have larger polyps or smaller polyps. So when we combine both long and local relationship, that actually helps.
Okay, thank you.
Okay, so that makes sense.
Yeah, I believe so. Like we don't have any follow-up questions, so maybe we can move on to the next topic. Yeah.
Sure. So next, I would like to introduce you with like our next work. So where we try to optimize or make the segmentation more efficient using graph convolution attention. So instead of using general or normal residual convolutions, here we try to use graph convolutions. So that our model actually can keep the long range relationships captured by the vision transform encoder in the decoder as well. So in this case, we use a similar kind of encoder, but we come up with again the decoder. The design of the decoder contains graph convolutional attention module, where we use a graph convolution block. So graph convolution block contains the graph convolutions, which has the message passing capability, and that helps to actually capture long range relationship among the different passes of the features. So this is one thing. Another thing, we also you like include the special attention here as well, so that our model also learn the special relations. So combining these two, it can actually refine the feature maps very efficiently due to using point-wise convolutions, as well as using a special attention that's very also efficient, but it has like better representation ability than even our cascade. So we use our Gcam block in 4 different stages, and we also optimize the up convolution block here using depthwise convolutions instead of using standard 3 by 3 convolution. So we did the same for outputs and do different kind of like loss aggregation here. So instead of using deep supervision of only 4 outputs, in this case, we try to utilize multi-stage Fisher mixing loss aggregation, where we actually do the combinatorial loss aggregation. So for example, we have 4 outputs. So we merge them together using combinations of them. For example, 2, 3, or 4 of them combining together. And for example, in case of n equal 4 stages, we get to the 4 minus 1, 15 synthesized prediction maps generated by our, we call this method mutations, our mutation. And we actually optimize this combined loss together. So this helps to improve the generalization ability and robustness of the model without like any overhead during the inference. Although like during training there may have just loss calculation overhead, but during inference we doesn't have any overhead. So here is our component evaluation, and based on this, we can see that like in this case as well, when we use graph convolution block as well as special attention module, all this combined, we get the base dice score 83.3% in this case. So over our baseline encoder, it improves around 3.2% with just only 1.78 million additional parameter and 0.342 gigaflops. Now we'd like to compare with our cascade. So here we actually did two different kind of comparisons. One is the our up convolutional block that's optimized over the cascade. So in case of cascade, it was more complex, having higher flops and parameters. But in this case, it's lower flops and parameters. And in our G-CASCADE, if you see, it even improves over the G-CASCADE with original number or original up convolution block with 3 by 3 standard convolution. So it reduces the number of parameters and flops, but it achieves better dice score. So compared to the cascade, we get better dice score with significantly lower parameter and flops. That's around 80% reduction in flops and 82.3% reduction 82.3% reduction in flops and 80.8% reduction in parameters. Yeah, so I think we may have another question. So
Yes, I believe it's a follow-up to the previous question. Was it possible to visualize such long-range importance in one frame or throughout the video?
we do not have that here, but I think we can visualize some of the segmentation outputs that may actually answer the questions, but I don't have right now in my slides, but it can be done like
It can be done.
analyzing
Okay.
it. Yeah.
Okay.
So yeah, if there is any question here,
I guess, yes, we have another question. Is there a particular task or organ where you saw the best improvement by using the graph component?
the organ wise, sorry, I didn't.
Yes. Is there a particular task for which you saw the most improvement using the graph, or are you evaluating it for just one task?
No, we are evaluating it for like multiple tasks. So I will actually show the results in next slides together. So after
Okay.
explaining all the methods,
Okay.
so that we can compare even like inter-method comparison.
Okay.
So yeah, so yeah, we should like yeah, in multi-organ segmentation we have like better here. We did show the experiments here on synapse multi-organ segmentation. So
Mhm.
in those cases, graph convolution is doing better.
Okay. Okay. Thank you.
Yeah, so now I would like to introduce you with our next method. So in this case, we again optimize our cascade decoder, but with like different method. So in case of G-CASCADE, I would like to address like say one of the limitation of that is graph construction. So when we actually construct the graph, we were using k nearest neighbor graph construction that has inference latency related to that. So um, that one of the thing for the graph construction. Another thing, sometimes it may end up with like out of memory error if we have larger base size during training, as well as we have larger image size. So to solve that problem, we come up with the solution of the optimizing the cascade using another angle. So in this case, we are using lightweight convolutions, but with multiple scale kernels. So let's focus on our method. So we have the similar like structure. We use the p-timed encoder, ImageNet p-timed encoder. This is transformer encoder we use, but we can use CNNs or static space models as well. And then we develop our decoders. So the core component of our decoder is multi-scale convolutional attention module. So let's focus on our multi-scale depth-wise convolution inside our multi-scale convolutional attention module. So I'd like to first give hints of the computational cost of standard convolutions. So standard convolution, for example, with q by q kernel, for example, 3 by 3, here we mean q by q, it could be 3 by 3, 5 by 5, or 7 by 7, or even 1 by 1. So it has the number of parameter and max requirement of q square c square and edge height width into q square c square. So it depends on C score most. So in general, C value of C is higher, 32 to 64 even. It increases to more than thousands or like 1000 or even more. So in this case, when C increases, the computational cost of standard convolution increases significantly. So the one of the solution or efficient convolution method is depth-wise convolution. So where the computational cost is q square c instead of c square is c here, so it reduces the computational cost significantly in this case. So, but when you use depth-wise convolution, it actually reduces the performance of the model as well, as it cannot capture the intra-channel dependency. So to recap the performance, we come up with a solution that uses multi-scale depth-wise convolution. So due to using multiple scales, for example, here we use 135 in our experiments. So it can capture multi-scale context using multiple kernels. For example, even pointwise convolution like one by one, 3 by 3, and 5 by 5. Even we can extend it to larger as well. So now what is the parameter and flops requirements? Yeah, it has more parameter flops than the basic depth-wise convolutions. So it's p square, q square plus s square c, but it has significantly better representation ability. But it has lower number of parameter and flops than standard convolution. So our method improves over both of the like standard convolution and depth-wise convolution. In case of standard convolution, we improve our both accuracy and efficiency. But in case of depth-wise convolution, we actually improve in case of like accuracy or representation ability of the model. So here is our like MSDC we use on our MSCB. So this is actually inverted residual kind of a structure block where we first expand the number of channels, then do the multi-scale depth convolution, and then again we actually retrieve the output number of channels from here, and we have a residual connection, and we use that in our MSCAM. So MSCAM contains channel attention, spatial attention as well with our multi-scale depth convolution. That's significantly more efficient and better representation ability. And we made another contribution. So there's we optimize the attention gate here as well. So we introduce here large kernel group convolution that helps to capture larger context with smaller number of parameter and flops. So yeah, we have ablation study in our paper to show that yeah, it's better than even standard gating function with lower parameter and flops. Here is the component ablation again with for our MCAD. So if you see this, our MCAD, we followed the cascaded structure in all the cases on our architectures. In this case, we have the large kernel attention gate, grouped attention gate, and we have multi-scale convolutional attention module. So when we use all this together, we get the best IC score 83.63% with 1.91 million parameters, additional parameters over the baseline. Baseline here means the encoder. So we have the encoder performance 80.10%, and our decoder improved it to 83.63% with just only additional 1.91 million parameters and 0.381 gigaflop in this dataset. This result is on Synapse multi-organ segmentation datasets again. So, and individual organ segmentation, our MSCAM has larger impact. It actually improved from 81.02 to 82.86%, where LGAC has comparatively lower impact. And if we like to see the multi-kernel tricks effect, so we can see that when we use different kind of kernels 1, 3, or 5, so it has lower dice score in both Synapse and Clinic DB, multi-organ and binary segmentation task. And also when we use 135, we get the best dice score, although it's not significantly better than like when we are using 1357. So yeah, and we believe that depending on the task, we may need to actually adjust this parameter, the number of like convolution operations or kernels. So it may work in case of like other datasets or larger datasets with different kind of like maybe larger number of kernels or something. But in our case, in Synapse and Clinic DB and other few datasets, we have found 135 is working better than if we use just 1, 3, or 5, or 3, 3 even, or 333 kernel even together. Here is the comparison with our cascade. If you see, similarly, we have significant improvement over the cascade. We can reduce the cascade's computational cost by 79.5% in parameters and 80.3% in flops, but additional like improvement in the dice score as well. Yeah, so and here is another empirical observation that we'd like to show you. So this is here we actually show the impact of pre-training. So when we use the pre-training and not using the pre-training, so on ImageNet pre-training actually of the encoder, not the decoder. So if we use the ImageNet pre-trained encoder, it has better dice score around like more than 3.5% better dice score than the if we do not use the pre-trained weights. So in case of a smaller network as well as larger networks, we have two versions of our model here. So it's like significant, I think. So ImageNet pre-trained weight of the encoder impact or major effect on the performance gain as well. Okay, so anybody, I think there may have some questions.
Yes, I think one of the questions is about the architecture. What are the key differences from the Swine unit or Swine unit R?
Yeah, so the Swin unitar and Swin unit, those are different kind of architectures. For example, Swin unit, that's completely transformer based architecture. So it uses transformer based Swin encoder, and it also uses transformer blocks in the decoder as well. So it's completely Swin transformer based method, U-shaped method. And
Okay.
in the Swin unitar, so it's a bit different. So Swin unitar, it uses transformer based encoder, Swin encoder, but it uses the decoder that's based on UNET kind of decoder using residual connections. Yeah, I will actually in my next like contributions, I would like to actually address this concern. So we improve the swing UNETR as well. So that's for 3D segmentation task. So all these methods that I described so far, it it was for 2D segmentation, like 2D segmentation task. Yeah, so
Okay.
Swing it's also a hybrid method having decoder with convolutions and encoder with transformer. But the thing is, unitar decoder in the Swing unitar was the major bottleneck there, culprit there having higher number of parameter and flops that we
Mhm.
optimized in our next work. Yeah.
Okay. And I think one question is about the efficiency. How did you measure the efficiency compared to standard convolution?
Yeah, so here the efficiency we try to actually show the lightweightness actually. So
Okay.
that's why we actually measure the number of parameters as well as the like flops or max here. So to actually measure the lightweightness of the model. But in case of efficiency, there may have latency requirements. In our like recent works, we actually address those as well. So yeah, we are not actually using latency in these cases. Yeah. So we
Okay.
mean
And
So I have
efficiency.
one follow-up question, Ma'am, that if you use like parallel convolution
Mm.
compared to the standard convolution, how it is possible that your number of parameter is low?
Oh, so I think you missed one point. So let me go to that slide again. So we mean like compared to the standard convolution, we have
Mm-hmm.
a number of flops and parameters because standard convolution has C score. So that depends on the number of channels. The number of channels usually start with 32 or even for larger models 64 and it goes beyond like
Right.
1K even.
Hmm.
So so when we have larger number of channels, these parameters significantly higher for a standard convolution. But in our case, it's the factor of C, so it's not C score. So for example, if we have 64 channels, this parameter, like standard convolutions parameter, would be 64 times than the depth-wise convolutions parameters. But in our case, it's like just only 3 times the depth-wise convolutions parameters. We are not saying we improve over the depth-wise convolutions
Oh,
parameters.
okay, got it. Okay, okay,
Yeah,
got it.
we improve over the standard convolutions parameters. Yeah.
okay, and I think we have one question about your results table.
Mm.
What is the KL, KR, and PC? I think it's the next table, please.
Yeah, this one.
Yeah. No, no. Please keep going. No, there is yeah, this one. So, what is KLKR? I mean,
Oh,
aorta and liver is clear, but
sorry, I didn't actually put that in the slide. So means left kidney and right kidney.
a right kidney, and then PC,
This
SP.
is pancreas and GB is gallbladder. Yeah, I
Okay,
have for this, but yeah, this
okay,
means like different organs actually.
okay. And I think this can relate to which organ the model performs the best for. I think
Yeah, so
Ramon's question.
here
Yes.
we have like even another slide where we compare different methods as well. So that
Okay.
I will go now even. Yeah,
Okay.
I'll show some of those results. Yeah.
Okay.
So we conducted like now I would like to introduce just the experimental setup. We conducted experiments on different data like datasets, 14 different datasets for this 2D segmentation task, and that belongs to 7 tasks. And this includes a multi-class segmentation like abdomen organ and cardiac organ, as well as polyp or microscopic image or breast cancer segmentation, ultrasound, skin lesion or retinal vessel segmentation as well. And we utilize different evaluation metrics, including DICE, mean intersection over union, or hash drop in some cases. Also, we use in some of our paper accuracy, sensitivity, and specificity app, like in addition to these matrices. And in case of loss function, for binary segmentation task, we use binary cross entropy and mean intersection over union loss. Both are weighted. And we are, in case of multi-class segmentation, we use binary cross entropy with dice loss. So with weighting here as well. And encoders, in most of our methods, we utilize pyramid vision transformer V2. It's the standard B2 method and B0 tiny method, as well as we utilize MaxBit in one of our work. So here is the result summary of on 10 different binary segmentation tasks. So if you see these results, we have our method PBT cascade, PBT G-CASCADE, MCAD, different versions, and we can see that like our method, like in this area, having like lower number of flops, less than 10 gigaflops in case of all the methods. Even like the MCAD B01 is very tiny number of flops, and the best dice score we got using MCAD B2 having even around 5-6 like gigaflops. However, all other methods, in most of the methods, having even transunit, one of the popular method in this domain for 2D segmentation task, having higher number of flops, and in case of parameter, it has also higher number of parameters. So our methods in general can get better dice score than one on average in 10 datasets here. It's generalizable, that means. So but with lower number of parameter and flops. So this is test results. So we actually divide these datasets into 80% training, 10% validation, and 10% test. And with the best validation model, saved the best validation model and use that model to actually test on like 10 different test sets, and this is the average test results. Yeah, so I think this table will answer that question with like individual organs, like segmentation performance of the Z-cascade. So in this case, I showed the results on CNS multi-organ segmentation. So here we have different organs that's reported at the right. So GB, gallbladder, kale, left kidney, right kidney, liver, pancreas, SP, spleen. So these are different kind of organs. And in general, if we see PBT cascade improves over all other methods, including transunit, swing unit, and different kind of methods. We got 81.06% dice score with only deep supervision. And it's like trans cascade version, that's like we just actually replace the decoder of the trans unit with our decoder, we get 82.68% dice score on an average. And PBT Z cascade, it improves over PBT cascade 83.28%. And if you see different organ segmentation performance, we can see that like PBT cascade help to improve gallbladder segmentation dice score, liver segmentation dice score as well. It got the best dice score in these cases. In other cases, it's also doing better. For example, in case of left kidney, and when compared to like cascade, in case of like most of the organs, we are getting better dice score than the cascade when we use graph convolutions. And our PBT like MCAT, like larger one, having the best dice score, and it has like best dice score in some of the organs as well. Yeah, so does it answer that question, having like different organ segmentations, impact of the graph convolution in different organ segmentation?
Ramon, do you have any follow up. Yeah, so this clears up the question, but I think we have a couple of other questions which we should probably take care of right now. One was about the previous comparison of number of parameters and dice code that you were showing the plot. The question there is that unit plus plus seems to have lower number of parameters than unit.
Yeah,
Uh,
yes. It depends on actually how these models actually configured. So we use the standard
Okay.
unit having larger number of channels, but
Hmm.
unit plus plus they actually optimize the number of channels here as well. So
Okay,
making the model
more
like
efficient.
yeah more efficient.
Okay, and the other question was about comparison with NN unit.
Oh,
Were you able to compare with NN unit?
we didn't compare our 2D methods with the NN unit, but
Okay.
we have comparison of our 3D methods with NN unit. But I think I didn't report that in this slide. But in our paper, you can actually explore the performance comparison with NN unit. Yeah.
Okay. And another question is about, I believe, the results on the next slide. Was the performance gain statistically significant between you? Because I think they seem kind of close enough. So hence the question about statistical significance.
Yeah, the thing is like, yeah, the PBT Z-Cascade and PBT MCAD are not statistically significant difference. As I mentioned, like PBT cascades the improvement in two different directions. One using graph convolution, another using graph convolution has a few like drawbacks or limitations. That's why we introduced like fully convolution based another method using lightweight convolutions in the PBT MCAD in our MCAD. So the performance difference between Z-Cascade and MCAD may not be significantly different, but their approach is significantly different, and also yeah, that's the thing actually. Our MCAT helps to solve one of the limitation of the Z-Cascade having out of memory error due to larger batch size, as well as we can solve the like latency like limitations of the Zcascade for the graph convolution operations using k-nearest neighbor, calculating like distance between all the neighbors and then using find the k-nearest neighbor. So that's sometimes like more computationally complex. So we try to actually address that issue and come up with our MCAT. But from our cascade to other methods is significant difference, around 2-3% difference.
Okay. Okay. Thank you.
I have a quick question about the training data.
Mm.
Yeah. So you see, we see you have 18 CT scans used for training. Um, uh, like once total segmentator came out, they have this training data set of 1,000 about 1,000 CTs. Um, do you have any comparison between like that ground truth versus the synapse training data, especially like the quality of training data?
We don't have that. This is a very interesting question, and I think we can explore that in our future work.
Okay.
Right now, we actually do not have, but yeah,
Okay. Mhm.
we use the Synapse dataset here, and yeah, we use 18 CT scan for training and 12 CT scan for validation, and these are the validation results.
Okay, thank you.
Yeah. So now I'd like to show you a few visual results. So this data is taken from our Cascade paper, so we don't have results beyond that. So if you see these results, so the ground truth GT is the second column here, and we have our method at the end, last column. So in the right. So if you see these results, our method has significantly better overlap with the ground truth than other methods having we actually put like 5 images here so that it's not like cherry picked. So we randomly try to pick some of the examples having this kind of things, and yeah, we have found in case of like performance, most of the methods, even like poly PBT having false positives in some cases due to noises or artifacts. But in our method can actually show the robustness to that due to using attention as well as convolution based methods. So these are few larger polyp segmentation, and we have a few polyp segmentation examples with smaller polyps regions. In this case, we also see like our methods is actually doing better than all other methods in most of the cases. And it has in the first row we try to highlight it, and we see that like some methods like polyPBT, it has false positive, but our method doesn't have the false positive, so it overlaps better with the segmentation mask. And one thing that like in my previous question, I asked about the quality of the data, and I have found in some cases these data sets are not even higher quality. For example, polyp segmentation, I found some examples having like lower quality. So that could be the sometimes cases our like performance is not 100%. So our model try to learn the patterns, and in that case it's actually doing better. Yeah. So this is result. These are a few additional results from our MCAD. I think I need to actually do it faster. So in this case also we have the similar observations. Some methods has false positive, but our methods actually do not have doesn't have the false positive. And in case of multi-organ segmentation, left kidney is missed by like most of the methods in correct unit. Even our PBT cascade cannot actually capture the left kidney, but our PBT EMCAD can capture or segment the left kidney. So now I'd like to explore maybe very concisely our next work. So this is for 3D segmentation. So we come up with efficient decoding mechanism for 3D segmentation, and this work is accepted as highlight in CBPR 2025. So in this case, we systematically try to find out the major limitation of the existing, like computational limitation of the existing unitar-based architectures. So we have found 3D Xnet one of the unitar-based architectures, and this is similar to like Swin unitar or Swin unitar V2 as well. We see the similar observations, and we have found that among 632.1 gigaflop, 624.16 gigaflop come from the decoder, and similarly like parameters as well. So what is the main culprit or main bottleneck for this? We find out this high resolution stages used here, like convolution in the higher resolution stages. It is the main culprit. It's having 368 gigaflops just only is this 3 layers. But if you see the performance difference, 79.7 and 79.5, just 0.2% performance gap between these two. And if we go like even later stage 79.4 to 79.7, that means 0.3% drop in performance, but we can reduce 300 gigaflops if we just remove these 3 layers. As well as we have found that the parameters come from higher number of channels in the decoding stages as well. So for example, 384 or even larger channels, 768. So in those cases, we have higher parameters, red marked here. So we come up with like two strategy. One is strategic removal of the high resolution layers if that doesn't actually improve the accuracy that much, and also we can actually optimize this number of channels to a uniform number of channels, and we propose this architecture design, so having decoder with uniform number of channels, as well as we can actually remove like those two high resolution layers and just use the trilinear upsampling here, and that's actually giving us 79.3% dice score with just 93% reduction in flops in the decoder and 96.4% reduction in the parameters. So here if we see like stage wise, we remove the like high resolution stage, we remove 100% parameter and flops, and in case of other stages we can reduce as low as 74% parameter and flops, and in case of even in some other stages 92% flops. Here is our results on synapse 13 organ segmentation task using a similar data set, 18 images for CT scan for training and 12 CT scan for testing or validation. So if we see this, we extend our method not only for 3D XNet, we apply this for Swin unitar, Swin unitar V2, and MedNext, another like method. So this method is completely different than 3D net or swing based method. So MedNext is using fully U-shaped architecture. So in this case, we have 86% reduction in number of flops and parameters because it could be like larger, but we need to add one of the residual convolution block to actually reduce the number of channels to a specific number of channels. So however, if you see the accuracy of dice score drop here, in case of swing neuter, we drop just 0.3% dice score. In case of Sinner V2, it's a bit larger, it's around 0.8% drop. In case of 3D net, we have 0.4% drop, and in case of MedNext, we have 0.4% drop. But in all cases, we can reduce the number of flops and parameter that's more than 86%. Here is our like results visualization, and if you see these results, we highlighted in the second row here. So in these cases, if we go to the second example, so we have we found that the convolution-based methods, for example, 3D net or MedNext, they are actually doing great in esophagus segmentation. So they can actually identify that part, some part of this. And we have find out that 3D net with our method can do that, but in case of Swinnerter, Swinnerter cannot actually even identify the esophagus region on this region here, but in our method can identify the esophagus here, some part, not that much, but it can actually do some. But although it reduces the high resolution layers as well as also unify the number of decoder channels. So we believe this strategy can be used for all other U-shaped architectures as well. So reducing the computational cost depending on the computational requirement. I have a few minutes, I think. So do you have any question regarding this method?
I don't think we have a question from the audience, but I have a quick question on that. So yes, overall performance drop is like really, really small. So that is very interesting. But if you remove those larger convolution, do you think performance drop is coming from kind of a resolution issue, right? Maybe the model
Yeah.
is now missing smaller organs or
Yes.
smaller patches of the organs.
It comes from resolution issue, and we have found like in some cases, yeah, smaller, in case of a smaller organ. So we have that in our paper.
Okay.
So yeah, now we have found in some cases smaller organs are losing more. Yeah.
Okay.
And but the thing is like it's actually applicable for sometimes maybe tiny organs, not, for example, thin like hair like kind of things
Mhm.
that may actually lose more. But in case
Okay.
of like organs, even the smaller organs, circular or other kind of shapes,
Mhm.
it's not actually may not affected by this. Yeah.
Okay. Thank you.
So yeah, I think this is last few things. I will actually quickly go through this. So in this case, we try to not introduce a new architecture, but we try to actually improve the robustness of existing architecture. So we come up with like this method. So this is called, we call PPSAM, Perturbed Prompt SAM, and we presented in one of the CPR workshop with proceedings. In this case, we try to actually enhance the robustness of fine-tuning SAM model for polyp segmentation. For example, this is if you have a look here, our method has more than 90% IC score, and if we use the perturbation during inference, for example, this perturbation means we extend the bounding box. For example, you are a user and you are using a very larger bounding box during like inference, and the performance drops 10% when we have a 50 pixel increase in all sides of the original segmentation output. And if we have 100 pixel, it performance drops 23%. In this case, we fine-tuned already, but we fine-tuned using the exact tight bounding box extracted from the mask, segmentation mask. So we come up with the solution. We incorporate this bounding box perturbation during actually training. So this no perturbation means we are using the tight bounding box of the segmentation mask, but perturbation means we are extending them in different sides in variable way, variable perturbations. For example, in some cases 10 pixels, some cases 50 pixels, some pixels. It's a random perturbation. So we do incorporate this, and then that helps to actually improve the robustness of the model. So let's see that example here. So we have in case of 100 pixel perturbations, we have seen 16% improvement by our method. And in case of a 50 pixel perturbation during inference, we have seen 8% improvement in dice score. And one thing is 50 pixel when we have a 50 pixel perturbation in wall side up to, so in that case we get the like best dice score in case of 100 pixel perturbation, but it has in the start it loses performance as it's using like during training while having like larger perturbation. So that's why we actually recommend to use variable perturbation. So this, and we also try to show the future performance. So even like this is the zero shot, that means we just use the SAM pre-trained on general data and do the polyp segmentation, and we have seen when do we have perturbations, it's very much like susceptible to perturbation, like vulnerable to the perturbation, and its performance dropped to around 20%. So but when we actually do the fine-tuning with our method, so with just only 100 images, we can get closer to the optimal performance using 900 images in the dataset. So last but not the least one, so in this method, so this is like accepted in MIDL this year, and we try to actually do like another kind of data efficiency experiment here. So reduce the data set before annotation. That means, so we would like to first reduce the data set and then annotate the reduced data set. So we try to use the network science property communities in image simulated network. If you see this image, there is always communities in the image. For example, this is different images, this node means, and this edges means there there is similarity between these. And based on this, if we find the communities, the different color means different communities, and if you see like there are different kind of larger to smaller communities here. So our goal is to actually find out the representative information from each community and remove other informations. So here is our algorithm. So we first construct the image similarity network, and then we apply the community detection. We use the Luvian community detection method here, and then we keep p% nodes from each community and remove others, and that actually helps to capture the representativeness from each community. And also, as we are considering all the communities, it's also diverse. And here is some of the examples that our method retained and our method pruned. For example, our method retained the left image and pruned its similar image from the dataset. So we may not need to actually use both of the images as they contain similar information, completely close to each other. So these are few examples. This explains for other kind of images as well. And here is our results on KVAC datasets, and we have also results on SANSEC, very large dataset as well in this case. So if you see, our method can actually remove 56.2% data with just 0.5% lose in dice score. Here is the original dice score using all the images, and if we just remove using our method 56.2% data, it can reduce this with only 5.5% drop in dice score. But if we do it randomly, for example, randomly pick the same number of images, so random pruning, this gray line here, so it loses more performance. It loses more than 1.5% performance, so or 2% performance. So our method, another difference with the random is random may actually give you the best results, may give you the worst result as well, but our performance is always stable. So it's actually giving the representative sets that work well always. Yeah, so that's we introduced different kind of 2D decoders, also one of the 3D decoder and data efficient methods, PPSM and Prime. And our decoder can be used with all other architectures, hierarchical encoders as well, even recent state space-based models as well. And in future, we would like to incorporate self-supervised learning with our decoders, because our decoders right now are not pre-trained, so we may actually pre-train, and that may work even better. And we would like to come up with very ultra lightweight methods for point of care devices, so that in case of we can use like maybe just only few k parameter and flops, and that may work better in case of point of care segmentation tasks. And image synthesis generative model is one of the like game changer right now. For example, we have data scarcity, so our goal is to also we are doing currently focusing on this, producing high quality in medical data to extend the data set, and then actually do the segmentation or train our model using both real and generative data, so that our model works better and generalize well in different cases. And also we are exploring the use of multi-modal learning like vision language model for biomedical image analysis task. Yeah, that's all. So if you'd like to explore our course, so we have our course available in the GitHub. Thank you everyone for staying with me. If you
Thank you
have any,
very much.
yeah, feel free to ask and I'll be happy to answer.
Thank you very much, Mustafi. Before we open the floor for questions, I'd like the audience to give our speaker a virtual round of applause. It was a very interesting presentation. And now, if we have any questions, maybe we can take a couple of questions.
One quick question. Yeah, thanks for the great presentation. Very, very interesting work. Like you were talking about lightweight, and that's very relevant. So, for example, the NVIDIA Monai group, right? There are two NIMs, NVIDIA Inference Microservices, which is one is for generating synthetic CTs, right? But one of the problems we run in practice into it needs a GPU. Even for inference, it needs a GPU with 40 or 60 GB RAM, right? Or it needs, and the same problem for there is a 3D segmentation model for CT. I think it's called Vista 3D, and there's a Vista 2D for cells. But it's the same problem. Like most of us don't have an H100 available, right?
Yeah.
So yeah, whatever lightweight like you have in future directions, ultra lightweight networks that can run on a consumer GPU like a 3090 or even a 2080 or a 2090, that would be very helpful. Okay, thanks.
Yeah, that sounds too good. And this is a very, very interesting direction. Thank you so much for pointing out this. Yeah, I got like the one of the idea of as I said, like our FPDX 3D when I was last summer in NIS. So the NIS scientists were actually complaining about the computational complexity of the Swin unitar model. So they were using Swin unitar everywhere, and they're saying, oh, it's taking too much time and also too much GPU. So could you please come up with like efficient or lightweight model for 3D
Mm.
things? I had our MCAD and G-CASCADE, those are for 2D. So that's why I try to explore the Swin unitar and other such kind of architectures and come up with the FPDX 3D. I think this FPDX 3D, if you use with any U-shaped architectures, it can actually optimize the architectures well. And if you see our paper, you may find it actually sometimes improve the dice score in some simple task. Although like we actually reduce the computation, like remove the high resolution layer, we unify the number of channels in the decoder. But in simple tasks, for example, if FETA is one of the fetal brain tissue segmentation datasets. In that case, we got improvement, although we reduce the number of parameter and flops.
Thank you.
Yeah, yeah. Thank you so much. Thank you so much.
Thank you. So if we have no more questions, then I would like the audience to give another round of applause to our speaker. And if anybody has any questions later, I'm sure we can put you in touch with the author. Thank you very much, Mustafi.
Yeah, thank you so much. If you have any questions, just feel free to send me email. I will be happy to answer. Yeah.
Sure. Thank you. Thank you very much.
Thank you.